Hello and how are you? Welcome to this tutorial in which we are going to cover calculus. And basically calculus in this particular sense, it gets its other name called elementary calculus. So this basically what you're going to do, it's just but a summary of 3 topics into one, and they are covered under one umbrella called calculus. So I'm your tutor, Joseph Adeli. Shall begin by a quick word of prayer. Father, Lord in heaven, invite in this session that you're able to guide us. You being the greatest mathematician I've ever known, able to teach us in the stillness of your voice this particular concept. In Jesus' name I pray. Amen. So quickly, what consists elementary calculus? Elementary calculus basically covers area approximation, which if you check in your syllabus, area approximation comes under topic number 67 in that particular syllabus. We have differentiation, which is topic number 66. So basically differentiation, according to their syllabus, comes before area approximation, but in this case we're going to cover area approximation first, then in that order differentiation, then finally we have integration. Those are the last 3 topics of the mathematics syllabus, basically in the Form 4 syllabus, which is topic number 68. That's case. So we are going to begin in this tutorial with area approximation. So by the end of this topic, you should be able to 1. Approximate the area of irregular shapes by counting techniques. You should also be able to derive the trapezium rule. You should also be able to apply trapezium rule to approximate areas of irregular shapes. Apply the trapezium rule to estimate areas under curves. Be able to derive the mid-ordinate rule, and finally apply mid-ordinate rule to approximate area under curves. So basically, maybe you have just seen some quite weird terms. We shall be able to explain what they are and what they specifically mean and why we need to be able to learn them. It's good to be able to appreciate something from the first point of view. So you may just wonder, why area approximation? Now, area approximation is it's a norm to the level of education that we have, that everything you need to calculate its area, it must have a formula. That's almost like a norm. Everything that you have been calculating has a formula. This has been the trend always. We have always interacted with rectangles, circles, triangles, name them. They all have direct formulas of calculating their areas. But have you ever encountered a figure that you so wished to be able to determine its area, but you ended up banging on the wall to no avail due to lack of a formula? You might have an irregular figure, but you're just wondering, why can't I get the area? Or in more sense, maybe someone told you to get some particular values. For example, if you remember in Form 1, under the topic physics, there's a topic called Hooke's law. It's Form 1. Form 2, you have a topic Hooke's law, and you have been given a graph of the force against, for example, you have the force and against distance. You're being told now calculate for the work done. You are wondering, how can I get the work done? Basically, you are getting area so that you will be able to get that. But now imagine you have an irregular figure, but you are looking for the area, you don't know how. So friend, worry not, area approximation has come to your rescue. This is what area approximation deals with: calculation of area of irregular figures. So it basically, you'll find out that it's just a matter of collection of techniques that enable you do the particular area of that particular figure. So area approximation has the following techniques to be able to help you solve your dilemma. So they basically include: number 1, counting technique; number 2, simplification technique. Now I've just given them these particular terms so that you may just be able to sum them up in how they apply, but they are quite a number. But in this level, there are those that you have been restricted to by the curriculum. 1 is counting technique. Counting techniques, this one simply comprises of, you have, for example, a definite figure that you're going to use to approximate the area. You know its area in fact, or the dimensions. So basically, you fill those particular shape attaching themselves together in that particular irregular figure, and then calculate them or count them, those that are complete, those that are incomplete, and then mathematically come up with the approximated area. For example, in this format we often use squares, but you can also use triangles, whereby now you know the length of the square. For example, you may say it's 1 unit each. So if it's 1 unit each, calculate the number of complete squares. You'll know that their area is basically 1 square each, multiplied by the total number of complete squares, and then those that are incomplete, we approximate them to be half each. So those are some of the things that are under counting technique. We also have triangulation, whereby you may have triangles, number them, and then you have a total number of area. Simplification technique carries quite a number of them. One, we have triangulation still, we have trapezium, we have trapezoidal rule or ordinate rule. Triangulation, you find that it may also require you to get the area of that triangle, because a triangle, not all triangles will be able to get the area directly. So majorly it falls under simplification technique, but if you have all the data, you can also put it under counting technique. So you may be able to fill that irregular area with triangles, get the base, get the height, calculate the area of each triangle, ensure that they're uniform, then multiply the number of triangles that you have. Trapezium rule, trapezoidal rule, or ordinate rule, those are the two that we are going to focus here. But we are also going to figure out what counting technique just in a very short time, so that we're able to get it according to the syllabus. So let's dive into what we need. So the area of regular figures can be calculated using various formulas. That's what we began by looking at, and why we need area approximation. However, irregular figures can only be approximated using various techniques, which we have already seen. In triangulation, we always the irregular figure into appropriate triangles and summing up their areas. I believe I've tried to explain what that is. So basically, if you have an irregular figure, let me just come up with an irregular figure like that. So I'll basically come and subdivide this into various triangles and ensure that they are uniform. I'm just trying to focus with my cursor. It's quite difficult, but I have to work it out so that you're able to appreciate what I need. So for example, we fill up this particular irregular figure with the triangles, get the area, and because they're uniform, multiply by the natural number of triangles that you have. That's triangulation. Alternately, the irregular figures can also be drawn on a particular scale and the area approximated by counting technique. So for example, you may come up with a graph, draw your irregular figure there, and then because you are using squares, get the area of each square, get the total number of squares that you have that are complete, and then those are incomplete. The ones that are incomplete, you approximate them to half, and then you can be able to have the total area. Let's just look at what counting technique entails. So therefore, the area will be the sum of the full squares and the sum of the half squares to get the full area. Let's just look at what it is. So in this case, we have this particular irregular figure, and it's on a particular scale, each of these being a square, and each square we make it an assumption that it's 1 unit each. So the unit part depends with you. What will be the representation of what, or what will you mean by the unit? That will be upon you to be able to define that. But we'll now have this one as 1 unit. So we'll count the number of complete squares. So for example, here we'll have, for example, we begin here, I'll just mark that. If you count the total number of squares, you'll figure out that there are 18. So if to be able to appreciate that counting, seeing is believing, you may pause the video, count that, and then be able to appreciate what I have. So basically there are 18 complete squares there. So that's what I begin with, counting the number of full squares. There are 18, and then those that are incomplete, be it almost like, for example, this one, you find that I only chopped off a slice of it. You find that others are almost complete, but not. Others are very small. All of them are approximated to half. So basically, come to the half unit squares. I'll find that they are found out that there are 20. If I multiply that, I'll get the total area of each of those particular squares was 10 square units. then sum the two up, you'll find that the total area of this particular irregular figure is approximated to 28 square units. And that's basically what counting technique entails. Let us dive deep now into other now technical techniques. We begin with the trapezium or trapezoidal rule. It's the same thing. So by just looking at that particular name, what comes into your mind? Trapezium or trapezoidal rule? Basically, from this particular name, you'll figure out that this technique, from the name, we apply the use of trapezium. Trapezium is basically the plural. Trapezium is singular. So how do we do that? We get the total area by following the following techniques. 1. Subdivide the irregular region into trapezia. So you basically draw various trapezias inside so that you're able to get the area. But maybe one thing that you'll be able to appreciate when you do an example is that the higher the number of trapezias, the more accurate you are. We are going to look at this in some particular drawings that I have for you so that we're able to appreciate this. So the smaller the trapezius, so that you increase the number of trapezius you're going to use, the higher the accuracy, so that you minimize the areas that are left out because you cannot be able to draw trapezius in. And then after getting the areas of each trapezia, you sum up the areas of the trapezia, and that will translate into the area of the irregular figure. So basically it will be the total areas A1 plus A2 plus each of those up to AN. N simply means the total number of trapezius that you'll have. So the area A1, for example, A2 or AN is basically the area of each trapezius. So whereby each trapezia is calculated by a half h, which h is the height, into brackets the length, the shorter length and the longer length, the ones that are parallel, joined by that particular height. That's how we get the area. I believe that you'll be able to appreciate that much more when you do an example. So for example, if I just have an example of a trapezia here, this particular height h is what I'm speaking of, and here we have A and here we have B. I believe that one you know how to calculate the area of a trapezia. Now let's quickly look at what I simply meant by the higher the number of trapezius, the higher the accuracy. Let's take an example. Here we have an irregular figure, and I've drawn in various trapezius of various formats. But notice there are some areas left out here that are not attended. Now notice if I reduce the number of trapezius, those particular areas reduce. We have the red ones. Notice the red now minimize the loss of areas that were not accounted for. Let's appreciate it much more when we shade the regions. Notice now if I shade this particular region, here we now have the black region is whereby I have the trapezia, the first trapezius, and then the remaining portions is shaded red so that we're able to appreciate much more of what I said. If you have smaller trapezius, you will end up minimizing the loss, the accuracy increases. So ensure that when you are calculating the area or approximating the area by use of trapezoidal rule, ensure that you minimize the loss of unaccounted area. So this is whereby we apply on irregular planes. But what if in advanced technology like right now, you are asked now to be able to get the area of which you have been given all the data, for example an equation, you have been given a curve or something of the sort. How do you do it? That is more technical, that more handy. That's now what you need to be able to work on so that we're able to appreciate that much more. So in that case, we have a curve, for example, and that curve will be in the form of y is equals to ax squared plus bx plus c. Now you have been told to be able to calculate the area under the curve, under that particular curve. So basically you want the area that's under the curve and bounded by, for example, the line y is equals to 0, or basically the x-axis. It may not only be the x-axis but any other axis, but in this case we are focusing on the x-axis. How will we be able to do that? So first we begin by subdividing that area into trapezius. So basically subdivide into various trapezius, and those trapezius must be of uniform length. So we have them like that, and because it's in plane, I decide to be able to have a uniform length or height, which basically I term as h. So h is uniform for each of these trapezius, these 4 trapezius. And because I have 4 trapezius, notice that in the form of what you may term as a strip. So these are some technical terms in questions that you have to be able to know. We are going, instead of now saying you calculate the area of this irregular figure by use of trapezoidal rule with a number of trapezius, you shall be told use this number of strips. You have to know that each strip represents the shape that you have, or the shape you are applying to be able to calculate the area. We're going to also look at the ordinate rule, which comes with its own particular shape that aids it in area approximation. So here our strip part comes as the trapezia. So the trapezia now basically caters for that particular strip. We're going to look at more and more of what we simply mean. So each of those strips is bounded by a length, which is basically the y axis, or basically term it, we call it ordinate. Ordinate is simply the y coordinate. So the y coordinate is called ordinate. So basically each of them will be y like that, y1, y2, y3, y4, y5. Now how do you get each of these? We basically substitute the value of the x corresponding coordinate into this equation so that you're able to get the corresponding y coordinate. So basically substitute it there, you'll get that it's corresponding to the y axis. So if I substitute, for example, if it was 1 there, and you have the values of a, b, and c, substitute in this equation, you'll figure out the point y1 on the y-axis, which is basically the total height of this point. So each of them is done in that particular manner. So let's take note of the following. 1. The width of the trapezia is uniform, which is h. It's uniform for all of them. So that means between 1 and 2 is 1 unit, 2 and 3 1 unit, 3 to 4 1 unit, 4 to 5 1 unit. So h is equals to 1 unit. It must be uniform. That's something you need to remember. Number 2, there are 5 ordinates amidst 4 strips. I believe you can notice that. 5 ordinates amidst 4 strips. Each strip, we have 1, we have 2, we have 3, we have 4. 4 strips and 5 ordinates. I believe you can see the ordinates that I'm circling with a blue pen. So strips are 4, but ordinates are 5. So that's a formula that you should never forget. The number of strips plus 1 is equal to the number of ordinates in trapezoidal rule. So that's what you need to always keep at heart. How do you get the height? For example, the formula we use is h is equals to x2 minus x1 divided by the number of strips. So basically x2, I'm simply using x2 minus x1. x2 simply means the farthest or the last x coordinate that you are having minus the first coordinate. For example, in this case, the last coordinate x2 corresponds to 5 minus the first coordinate, which is 1, divided by the number of strips. For example, number of strips are 4. So if you divide by 4, you figure that you only have 1 unit. So this will be equal to 1 unit, which is basically what I said earlier on. Or you may say, I want to use the number of ordinates, which will be minus 1 to get the number of strips. So if you divide that, you will also get 1 unit. So that is something that you need to remember. Now with this data that we have, we can be able now to go forth and derive the formula. Let's begin working out. We know that the total area by using the trapezoidal rule, because you're using trapezius, it will be the summation of each of those trapezia, the area of each trapezium separate, and you sum them up into this formula to be able to get the total area. Now, how do you want to subdivide each of those parameters a1, a2 up to an to be able to get our formula? We'll be able to appreciate this, that the first trapezia, its area is here, a1, a2, a3, and then a4. It is simply the same format. So I believe you can be able to follow up slowly. Now I want you to open up this particular equation, simplify it up to the most simplest possible. so that you're able to appreciate what the next step I'm going to do, because for me I summarize it very quickly. But if you are quite slow in algebra, it will be important for you to just do it slowly before we will go to the next step. Now, you'll appreciate that a half h is common to each of these expressions. So notice we have a half h here, we have a half h, we have a half h again, we also have another half h here. So it means because it is common in each of those expressions, it can basically be what you term as a scalar for each of those expressions. So basically I'll come and say that a half h is multiplying each and every parameter that's inside this bracket. But notice that there are some parameters that are twice. y2 is in this particular point, and we also have here y2. So basically I have 2y2. We have 2y3 because y3 is twice, y4 is also twice. But y1 and y5 is what it's what is in a single form. So that's what we have here. So if I simplify it further, I'll be able to come up with this formula. Half h into greater brackets, we have y1 plus y5 plus twice of y2 plus y3 plus y4. But from this, notice that we know that the number of strips plus 1 is equal to the number of ordinates. So I can simplify this one now, because not all times I'll be able to have 5 ordinates. I'll be having, for example, 2 ordinates, 10 ordinates, depending with the format of the equation. So I'll simplify the equation more easier now to say that half h is equals to y1 plus yn plus 1, where n is the number of strips, plus 1 giving me the total number of ordinates, plus 2 into brackets y2 plus y3 plus y4 plus any other ordinate that I'll be having, all of them summing up to yn. Then yn, we don't even know what yn is. For example, n here is 4. We know the number of strips are 4. So basically n will be equal to 4. But if I come to this particular format, we know where I derive those particular n plus 1 and n from, so that it may be able to give me a constant formula for all questions that I'll be approximating area by the use of trapezoidal rule. So whereby we know that h is equals to the last x coordinate minus the first x coordinate divided by the number of strips, or basically x2 minus x1 divided by the number of ordinates minus 1, and n number of strips plus 1 is equals to n ordinates. Those are very good parameters you should never forget with trapezoidal rule. Let's do an example with that. So I've basically given you here the image that you basically have in your log tables, so that you're able to appreciate it much more better. Notice that here we now have them up to y7. So it means n plus 1 is 7. We have 6 strips, and that format you can be able to apply it here. Let us do an example. You may pause the video if with the information that you have, I believe you can try to fumble up with this question so that you're able to get what it is. Now you have been told, estimate the area bounded by the curve y is equal to x squared minus 3x plus 6, and we have x minus 1 and x is equals to 3, and the x-axis using trapezoidal rule with 8 strips. So basically it's bounded by each of those parameters. It starts from x equals to 1 to x equals to 3, x equals negative 1, sorry, and you are going to apply 8 strips. Now remember, trapezoidal rule, if you have 8 strips, it basically means we are going to have 9 ordinates. I believe that is ringing in your mind. Now the solution part. So we know that n ordinates is equals to n number of strips plus 1, which will have as 9 ordinates. So by that, after getting that, we can get the interval or the length or the height of each trapezia, which will basically be 3 minus negative 1 divided by 8 strips, which will basically give us 0.5 units. So that is the length of each trapezium. So by using this particular equation, we shall now be able to get the corresponding ordinates. We need to get the ordinates part. So we shall come up with this table, and to fill each particular y parameter here, or each y coordinate, we shall be able to substitute each x value into our equation. So each of these, if you substitute them, you will be able to have those particular values filled like that. So if you substitute -1, you'll have 10, negative 0.5, 7.75, all the way up to 3, which will be 6. Then come up with your formulae, substitute each and every point here. So y1 will be 10, n plus 1 will be 6. Basically, that's what I simply came up with. And each of that, you'll end up with 21.55 square units. Basically, substitute each and every of these into that. So basically, you start counting from here. This is y1, this is y2, y3, y4 up to 6, which will be y9. That's basically that, and the total area will basically be 21.55 square units. This part must be remembered. That is something that you must remember all through. There's nothing that can never miss units. So if you have the actual units, for example, square centimeters, square meters, you substitute it there. But if you don't, ensure that this part does not miss out square units, because it's also another area measuring unit. Let us go to the next rule, mid-ordinate rule. In mid-ordinate rule, from the name that comes out, what comes into your mind? Mid-ordinate rule. That's something we just want to ask you. Notice, from the name, we denote the following. 1, ordinate. What is ordinate? It's the value of a coordinate on the vertical axis, which is basically the y-axis. Mid simply means occupying a middle position. Now, if you combine the two, mid-ordinate, what do you come up with? Mid-ordinate simply means the value of a coordinate on the y-axis that occupies a middle position. So in this case, we are working with something that is, we have two x coordinates, and in between them, we have a midpoint, and that midpoint will be able to give us what we call a mid-ordinate point. So let me just try to sketch what I mean here. So we may have this, and you have your point 1 here, and you have another point 2 here. That means I'll come up with another point 1.5 in between here, which will end up giving me another ordinate that is in the middle. I believe you can see what I mean there. So we have this ordinate and that ordinate, but we are working with this one that is in between, this one here. That's what we simply mean by mid-ordinate rule. And in this case, notice that in my area approximation, I'm coming up with something known as a rectangle. We're going to apply that in this case. So that's something you need to note. Now, NB, not below, the ordinate part of this rule applies only when we have a grid or a graph. So unless you have the two, mid-ordinate rule, we shall be able to only apply it in approximation directly by using rectangles and all other things. But if you have a grid or a graph, the rule part, which basically will now have you to pick out what is the ordinate part, shall apply in this particular rule. Let's quickly look at the part of approximating approximations. So I believe I've spoken about this. We apply by use of a rectangle. In this area approximation technique, we apply the use of a rectangle to be able to get the total area of the irregular figure. We basically apply the following steps. 1, subdivide the irregular region into rectangles, and something you need to note also, the more the number of rectangles, the more the accuracy. Sum the areas of the rectangles. The sum of the areas of the rectangles translate into the area of the irregular figure, which basically means the total area is equals to A1 plus A2 plus all of them up to AN, whereby the area of each rectangle units the product of length and width. Let us look at why we say the summation of the more the number of rectangles, the more the accuracy. Notice here, we have also some regions that are left out when we apply the rectangles. But if I bring out more smaller rectangles, this is what I may end up with. I cover quite a large number of area. I believe this one now is even more clearer when I shade out the regions. So that's what you need to remember. The more the number of rectangles, the more the accuracy or the more accurate your value is. Let us get the more professional version of this mid-ordinate rule. We want to derive our equation. So basically, have that graph. We in the form of y is equals to ax squared plus bx plus c. How do you go about it? Split each of them into rectangles. So first, we draw complete lines from that particular line at a uniform length h from the curve downwards, and we extend dotted line upwards so that we are able now to trace where shall our rectangle reach, because in this case we need to have it in the middle. So notice, when we are approximating the area, we have to also to minimize the area loss. For example, if my rectangle were to reach at this line here that I've drawn here, notice I'll end up having a very big area that is not accounted for in my answer, which will give me a wrong value. Or I may end up deciding to say now, so that I may only have a total area that is basically what I want, I then have my rectangle up to that point, which will not be the case still, because I'll miss out this area that is remaining here. So to increase my efficiency to 50% so that I don't miss out any area that I need to get, what I basically do, I'll ensure that the area that I leave out and the area that I calculate for is almost at a 50% efficiency. So my rectangle shall reach up to that point where the green line reaches, or when the green line passes, such that my ordinate drops directly in the middle. So notice that I'll have missed some area on the top side here, and I'll have also left out a considerable amount of area that is not to be calculated upwards there. I believe it makes more sense. So basically, after that, we basically drop ordinates at each particular point, and then ensure that we also ensure that we have our rectangles ready by drawing complete lines here. So basically, how do you get those points? Basically, you also substitute them into the equation that we have. And you know that if you have the graph already there, you can be able to read it directly from the y-axis. Or if you don't, if you are just sketching, you can just punch your x values into this equation. You will get the corresponding y ordinates. And I would like you to take note of the following. The width of the rectangles, sorry that I have here what we term as trapezium, it should not be trapezium, it should be rectangle, is uniform in this format. So notice at each particular point we have 1 unit, 1 unit, 1 unit. That's something you need to note. Number 2, there are 4 ordinates amidst 4 strips, which are the rectangles. So there are 4 ordinates and 4 strips. So y1, y2, y3 up to y4, and you also have 4 strips of rectangles. So that's one expression that we should not forget. Now, how to get h is still the same format, but in this case, when you are applying the number of ordinates, because they are equal to the number of strips, it will the formula still remains the same: x2 minus x1 over n, of which n is the number of strips. So with this, let's derive a formula. The area, total area of by use of mid-ordinate rule, is basically a1 plus a2 plus a3 plus up to an will basically give us the total area. But now, what do these a1 and a2, a3 represent? They are basically the areas of each of these strips, or basically the rectangles, which is h multiplied by y1 plus multiplied by y2, y3, like that. But notice the h part is constant all through, and it is similar. So it shall then give us our scalar or the multiplying factor. So basically it will be h multiplied by y1 plus y2 plus y3 up to y4. So with this, we can be able to derive the final formula that shall apply for all area approximation technique by use of mid-ordinate rule, which shall basically come to h into y1 plus y2 plus dot 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 up to yn, whereby n is the number of strips or basic number of ordinates because they are equal. So this shall be the formula that shall apply all through. If there's a challenge, please pause to be able to digest whatever we have just done up to this case. So whereby h, you know, h is the basic length, or you can call it width depending on how you want to view the rectangles, and n, the number of strips, is equals to the number of ordinates. Let's now dive into an example, but before that I have this diagram for you, which basically I got sourced it from your logarithm tables, so that can be able to help you out in practicing even more. An example directly, still the one that we had. Estimate the area bounded by that curve. If you don't mind, we pause the video so that you're able to work it out together, so that you may compare it with what you have and compare with what I'll have. The solution. In this case, we know that the number of ordinates equals the number of strips. Basically, we'll end up having 8 ordinates, because in the equation have been bounded to use 8 strips. Sorry for this particular mismatch, it should be mid-ordinate rule. So basically h will basically be a half, 0.5 units. So I'll end up come up with that particular equation, come up with my table, get the y ordinates, and that's what I'll end up with. After getting those y ordinates, substitute them into my equation, and I'll end up getting my area as 21.25 square units, and that will be the total area that I'll have for this particular case. So that's all that we had. Success in your preparations. May God bless you abundantly. In the next tutorial, now we shall begin diving deep into differentiation and integration as we wrap up this particular topic called calculus, or basically elementary calculus. If you'll have a yearning for more examples, we shall be able to sort that out later, so that you may have more examples to be able to cater for your practice. May God bless you abundantly.